the sun, the heart of our solar system. This giant ball of burning gas is vital to life on Earth. It provides us with light and warmth. But what is this celestial wonder made of? Let's take a closer look and unveil the secrets of our star. The sun is not a solid mass like the Earth. Instead, it's a giant ball of plasma. Plasma is a superheated state of matter. It's similar to gas, but the atoms are stripped of some of their electrons. This makes plasma electrically conductive. Understanding the sun's composition helps us understand how it works. It also helps us understand other stars in the universe. The sun is our closest star, so it offers us a unique opportunity for observation and study. The sun is mostly hydrogen and helium. These are the two lightest elements in the universe. Hydrogen makes up about 70.6% of the sun's mass. Helium accounts for about 27.4%. Hydrogen is the fuel that powers the sun. Deep within its core, hydrogen atoms fuse together. This process, called nuclear fusion, creates helium and releases an enormous amount of energy. Helium, the product of fusion, is itself a fascinating element. On Earth, we know it as a gas that makes balloons float, but in the sun's core, helium exists under extreme pressure and temperature. The remaining 2% of the sun's composition includes heavier elements. These include oxygen, carbon, neon, iron, and others. While small in proportion, these elements play a role in the sun's overall behavior. Let's imagine we could journey to the center of the sun. We'd encounter different layers, each with unique characteristics. The journey would be perilous, but it would reveal the sun's inner workings. At the very heart of the sun lies the core. This is where the magic happens. The core is a dense, extremely hot region. Temperatures here reach a staggering 27 million degrees Fahrenheit. The immense pressure and temperature in the core create the perfect conditions for nuclear fusion. Hydrogen atoms are forced together, overcoming their natural repulsion. This fusion process releases the energy that powers the sun. The core is about 25% of the sun's radius. Don't let its size fool you though. The core is incredibly dense. It contains about half of the sun's mass. Moving outward from the core, we encounter the radiative zone. This layer is named for the way energy travels through it. Radiation. Photons or particles of light carry energy outward. Imagine a crowded room where you pass a message by whispering it from person to person. That's similar to how energy travels through the radiative zone. Photons are constantly absorbed and re-emitted by the dense plasma. It takes a very long time for a photon to escape the radiative zone. Scientists estimate it can take hundreds of thousands of years. This is because the photons travel in a zigzag pattern, constantly interacting with matter. The temperature in the radiative zone decreases as we move outward. It ranges from about 12.6 million degrees Fahrenheit near the core to about 3.6 million degrees Fahrenheit at its outer edge. Section 5. The convective zone, bubbles of plasma. Next we reach the convective zone. Here, the energy transport mechanism changes. Instead of radiation, convection takes over. Think of a pot of boiling water where hot water rises and cooler water sinks. In the convective zone, hot plasma rises from the bottom, carrying energy outward. As it cools, it becomes denser and sinks back down. This creates a constant churning motion, like a giant pot of boiling plasma. These convective currents are responsible for transporting energy from the radiative zone to the sun's surface. They also play a role in generating the sun's magnetic field. The convective zone is about 100,000 kilometers thick. It's a turbulent region with constantly shifting patterns of rising and falling plasma. Section 6. The photosphere, the sun's visible surface. Finally, we reach the sun's visible surface, the photosphere. This is the layer we see from Earth. It's a relatively thin layer, only about 400 kilometers thick. The photosphere is where the sun's energy is finally released as light and heat. It's a dazzling display of activity with constantly shifting patterns of light and dark areas. One prominent feature of the photosphere is granulation. These are small, bright cells that cover the surface. Granules are caused by the convective currents in the layer below. The photosphere has an average temperature of about 9,940 degrees Fahrenheit. While this is cooler than the inner layers, it's still hot enough to vaporize most materials. Section 7. Solar atmosphere, chromosphere, and corona. Above the photosphere lies the sun's atmosphere. This region consists of two main layers, the chromosphere and the corona. These layers are usually invisible to us, but they become visible during a solar eclipse. The chromosphere is a thin layer of plasma above the photosphere. It's named for its reddish color, which is only visible during a total solar eclipse. The chromosphere is hotter than the photosphere, with temperatures reaching 36,000 degrees Fahrenheit. The corona is the outermost layer of the sun's atmosphere. It extends millions of kilometers into space. The corona is also much hotter than the chromosphere, with temperatures reaching millions of degrees Fahrenheit. Scientists are still studying why the corona is so much hotter than the layers below it. Both the chromosphere and the corona are dynamic regions with various features. These include prominences, which are huge arches of plasma, and coronal mass ejections, which are massive bursts of plasma and magnetic field. Section 8. Solar flares. The sun's explosive temperament. The sun is not always calm and steady. It can unleash sudden bursts of energy known as solar flares. These are powerful events that can have significant effects on Earth. Solar flares occur when magnetic energy stored in the sun's atmosphere is suddenly released. This releases a burst of radiation across the electromagnetic spectrum, from radio waves to X-rays and gamma rays. When a solar flare erupts, it can interfere with radio communications on Earth. It can also disrupt satellites and even power grids. The most powerful solar flares can be hazardous to astronauts in space. Scientists are constantly monitoring the sun for signs of solar flares. Predicting these events helps us prepare for their potential impact on our technology and infrastructure. Section 9. The sun's gravitational embrace. The sun's immense mass gives it a powerful gravitational pull. This gravity is what holds the Earth and all the other planets in our solar system in orbit. Think of the sun's gravity as an invisible tether, keeping the planets from flying off into space. The planets are constantly being pulled towards the sun, but because they are also moving sideways, they fall around the sun instead of crashing into it. The strength of the sun's gravitational pull decreases with distance. That's why planets closer to the sun, like Mercury and Venus, have shorter orbits than planets farther away, like Mars and Jupiter. The sun's gravity also affects objects beyond our solar system, influencing the paths of comets and other celestial bodies. Section 10. Solar wind. A stream of charged particles. The sun doesn't just emit light and heat. It also constantly releases a stream of charged particles called the solar wind. This wind flows outward from the sun, filling the solar system. The solar wind is made up of mostly protons and electrons. These particles travel at incredibly high speeds, reaching millions of kilometers per hour. They carry with them a small part of the sun's magnetic field. When the solar wind reaches Earth, it interacts with our planet's magnetic field. This creates a protective bubble around our planet, shielding us from most of the harmful radiation. However, the solar wind can also have some beautiful effects. It's responsible for the auroras, also known as the northern and southern lights. These dazzling displays of light occur when charged particles from the solar wind interact with gases in Earth's atmosphere. Section 11. Atomic energy, the sun's powerhouse. At the heart of the sun's energy production lies the incredible power of atomic energy. Specifically, it's nuclear fusion that fuels our star. Nuclear fusion is the process of combining lighter atomic nuclei to form heavier ones. In the sun's core, hydrogen nuclei, which are simply protons, are forced together under immense pressure and temperature. This overcomes their natural electrostatic repulsion. When the hydrogen nuclei fuse, they form helium nuclei. This process releases a tremendous amount of energy, according to Einstein's famous equation, E equals mc squared. A tiny amount of mass is converted into a vast amount of energy. The energy released by nuclear fusion in the sun's core is what powers the sun and provides the light and heat that sustain life on Earth. It's a remarkable example of the incredible forces at work in the universe.